At the heart of every black hole lies a secret where physics itself breaks down. We are about to journey through 30 staggering unknowns that challenge everything we think we know about these cosmic giants. You will discover the deepest puzzles of space and time, from the fiery fate of information to the possibility of hidden universes. What truly happens when you cross a black hole's edge? And could they be rewriting the laws of reality itself? What single mystery about the cosmos keeps you wondering late at night? Our journey begins at the very center with the ultimate unknown. The singularity is the black hole's final secret, a point where all the collapsed matter is crushed into an infinitely small, infinitely dense pinprick. Think of it as the ultimate dead end for physics. Our most trusted map of the universe, Einstein's theory of general relativity, predicts this point of infinite curvature, but the math simply stops working there. It is as if you are following a trail into a cave and the path suddenly vanishes into a bottomless pit. The equations spit out infinities, which is the universe's way of telling us we are missing a crucial piece of the puzzle. This is where the other great pillar of physics, quantum mechanics, shouts in protest. It insists that information cannot be truly destroyed and that such a point of infinite density should not be possible. So we are left with a fundamental conflict at the heart of reality. The quest to solve this is the search for a theory of quantum gravity, a single framework that can marry the vast cosmic scales with the bizarre rules of the quantum world. What truly happens in that realm of pure curvature, where space and time as we know them cease to exist? The answer remains one of the greatest unsolved mysteries in all of science. This paradox strikes at the very laws that govern our universe. What happens to the information about an object when it vanishes into a black hole? Quantum mechanics insists that information is never truly lost. It can be scrambled, transformed, but never erased from existence. Think of it as the universe's ultimate cosmic ledger, where every detail is permanently recorded. Then Stephen Hawking made a startling discovery. He realized that black holes are not entirely black. They slowly leak radiation and over immense stretches of time can completely evaporate. This process seems to create a catastrophic problem. If the black hole vanishes, what happens to all the information about every star, planet, or book that ever fell in? It appears to be permanently deleted, violating a foundational rule of physics. It is as if you could burn an encyclopedia, and the information within it is not just transformed into heat and ash, but utterly annihilated, erased from reality itself. This is the information paradox. One compelling solution suggests that information is never actually lost because it is never truly inside the black hole in the first place. The holographic principle proposes that all the information about what falls in is encoded, like a cosmic fingerprint, on the two-dimensional surface of the event horizon. The three-dimensional interior we imagine is just a projection of that data, a hologram. So when the black hole evaporates, that information is slowly and chaotically released back into the universe, hidden within the Hawking radiation. The encyclopedia is burned, but the information survives, imprinted impossibly onto the smoke. This solution, however, creates a new and perhaps more violent mystery. What if the event horizon is not a smooth, invisible threshold, but a wall of fire? The Firewall paradox presents a terrifying possibility. To preserve the law that information cannot be destroyed, physics might demand a radical rewrite of what happens at the black hole's edge. The idea suggests that just inside the event horizon, a seething curtain of unimaginably high energy particles lies in wait. An astronaut falling into a black hole, expecting to cross smoothly into the unknown, would instead be instantly vaporized by this energetic barrier. Every atom would be torn apart in a flash of intense radiation. This is not just a dramatic idea, it is a direct challenge to a cornerstone of Einstein's general relativity, the principle of equivalence. This principle assures us that if you are in free fall, you should feel no forces. You should not even notice you are crossing the point of no return. The universe should feel smooth. A firewall shatters that completely. It places a glaring, violent signpost at the boundary, something you would absolutely notice or rather be obliterated by. This has sparked one of the most intense debates in modern theoretical physics. One camp argues the firewall is a necessary consequence of protecting the laws of quantum mechanics. The other insists it is a sign that we have made a grave error in our reasoning, that our understanding of how quantum theory and gravity mix is still profoundly flawed. The very nature of the event horizon is now in question. Is it the tranquil gateway relativity describes, or is it the universe's most destructive security system, a blazing perimeter guarding its deepest secrets? The debate continues to burn as brightly as the hypothetical firewall itself. But the firewall is not the only paradox waiting at the edge. Beyond the question of what destroys an object lies the deeper mystery of what actually becomes of it. When matter is pulled past the event horizon, where does it go and what is its final state? Our best theories suggest it is doomed to travel inward, inevitably crushed and merged into the central singularity. Yet some physicists wonder if that is the whole story. Could the matter's information be somehow stored, its essence preserved on the horizon's surface while its physical form is annihilated? We are left with two grim possibilities, either total destruction at a point of infinite density, or a transformation so complete that the very concept of matter loses all meaning. This puzzle of ultimate fate is intimately tied to another breathtaking idea, the possibility of a cosmic shortcut. The same equations that predict black holes also allow for the existence of wormholes, theoretical tunnels through the fabric of spacetime. Often called Einstein-Rosen bridges, these are not the black holes we observe, but rather a different solution to the math. Imagine a black hole not as a bottomless funnel, but as a tube connected to another point in space, or even to another universe entirely. Instead of a dead end, it would be a bridge. The immense gravitational crush at the center of a black hole would, in this speculative picture, open up into a new region of space-time, a passageway offering a journey of incalculable distance in a single step. Yet this incredible concept comes with a universe-sized catch. These theoretical wormholes are predicted to be violently unstable. They would snap shut in an instant, far too quickly for anything, even light, to traverse them. To hold a wormhole open, to make it a practical gateway, would require a substance with truly bizarre properties, something known as exotic matter. This is not antimatter or dark matter, but a hypothetical material that possesses negative energy or negative mass, effectively pushing spacetime apart rather than pulling it together. No such substance has ever been observed, and whether it can even exist is a major open question. So while the mathematics of relativity paints a picture of these fantastic tunnels, the physical laws as we understand them seem to forbid their use. The fate of matter and the existence of wormholes remain two of the most profound spacetime mysteries, forcing us to ask whether a black hole is a cosmic trash compactor or the locked door to a universe next door. Black holes might have a hypothetical twin, a complete opposite known as a white hole. If a black hole is a cosmic drain from which nothing can return, a white hole would be its gushing fountain, a region of spacetime that endlessly expels matter and energy while forbidding anything from ever entering. This concept emerges beautifully from the mathematics of general relativity, essentially as a black hole playing the film of its life in reverse. Yet for all its mathematical elegance, most physicists doubt white holes exist in our reality. The reason is entropy, the universal trend toward disorder. A white hole spontaneously appearing and spewing out ordered energy would seem to violate this fundamental cosmic rule, making it a breathtaking theoretical idea that our universe appears to have rejected. While a white hole represents a reversed flow of time, the process that seals a black hole's eventual fate operates on a much smaller scale. Hawking radiation is the slow leak that causes even the mightiest black hole to evaporate over eons. To understand this, we must venture into the bizarre quantum realm that exists even in the vacuum of empty space. Here, pairs of virtual particles constantly flicker in and out of existence, borrowing energy from the void for a fleeting moment before annihilating each other and repaying the debt. This strange quantum dance happens everywhere, but at the event horizon of a black hole, it takes on a cosmic significance. Imagine one of these particle pairs appearing right at the precipice. In a stroke of terrible luck, one particle falls across the event horizon, while its partner escapes into the vastness of space. The escaped particle becomes real, stealing a tiny amount of the black hole's mass energy to pay its debt to the universe. This is Hawking radiation. From the outside, it looks as if the black hole is glowing ever so faintly with this stolen heat. For a supermassive black hole, this process is incredibly slow, but for a smaller one, the radiation would be more intense, leading to a runaway evaporation that ends in a final, silent pop. This subtle quantum theft is how a black hole, the most gravitationally dominant object imaginable, meets its end not with a bang, but with a whisper of particles born from the void itself. This elegant simplicity is known as the no-hair theorem. It suggests that a black hole is the universe's ultimate blank slate, defined by just three numbers: its mass, its electric charge, and its spin. Everything else, every intricate detail about the stars, planets, or civilizations that fell in, is permanently erased. It has no hair, no unique features, no memory of its violent past. But is this cosmic barbershop truly perfect? Many physicists suspect this theorem might be an approximation, a beautiful simplification that breaks down under the full, messy scrutiny of quantum gravity. They propose that information about what fell in is not destroyed but is instead scrambled and stored on the event horizon itself, a subtle form of quantum hair that gives each black hole a unique, if invisible, identity. This debate strikes at the nature of reality itself. Are black holes the simplest objects in the universe, or are they the most complex, their inner histories hidden behind a veil of apparent simplicity? Stepping through that veil leads to a place where physics becomes surreal. Beyond the event horizon, within the black hole's dark heart, the very roles of space and time are inverted. Outside the horizon, you can move freely through space but are carried inexorably forward in time. Inside, all paths lead downward. Your future is no longer a matter of choice. It is a location, the singularity at the center. Space itself behaves like a river flowing toward a waterfall, and you are caught in the current. In this bizarre interior, to move away from the singularity is as impossible as trying to travel backward in time in our world. You are not just pulled by gravity, you are riding the very fabric of space-time as it collapses inward at a pace that eventually exceeds the speed of light. The geometry warps into a funnel of impossible steepness, where distances stretch and compress in a final, violent descent. Imagine a corridor where the walls are not made of brick but of time, closing in from all directions until there is nowhere left to go. This is the inevitable crush that awaits, a destination written into the coordinates of the universe where the river of space-time simply ends. Long before the first stars ignited, the universe was a seething, dense soup of pure energy. In that primordial chaos, the most ancient black holes might have been born. These are not the stellar giants we know today, but hypothetical tiny specks, some no heavier than a mountain yet compressed into a space smaller than an atom. These primordial black holes are cosmic fossils, potentially formed from the intense pressure variations in the first moments after the Big Bang. Their existence would solve a profound modern puzzle. We know most of the matter in the universe is invisible, a substance we call dark matter. Could these countless ancient black holes, scattered like dust across the cosmos, be the hidden mass that binds galaxies together? The hunt for them is on, with astronomers searching for the telltale flash of light when one distorts a distant star or the faint ripples in spacetime they might create. Finding one would be like discovering a living relic from the dawn of time, a key to unlocking two mysteries at once. This connection between the vast and the tiny brings us to a concept that measures a black hole's hidden complexity, its entropy. In our everyday world, entropy is a measure of disorder, the reason a melted ice cube never spontaneously refreezes in a warm room. For a black hole, entropy is a number that represents all the possible ways its internal, scrambled information could be arranged. The astounding discovery made by physicist Jacob Bekenstein is that this entropy is not proportional to the black hole's volume, but to the surface area of its event horizon. Think of the universe's ultimate symbol of disorder, and its total chaos is written on its two-dimensional surface, not stored within its three-dimensional depths. This is a profound clue. It suggests that the event horizon is not just a boundary, but a fundamental data storage device. Every bit of information that falls in adds a tiny, permanent pixel to its surface area, increasing its entropy. This area law is why the holographic principle feels so compelling. It hints that the universe might fundamentally operate like a cosmic projection, with all the information needed to describe a volume of space encoded on its boundary. The immense entropy of a black hole tells us that it is not a simple, empty pit, but arguably the most disordered and therefore the most complex object in existence. Our universe seems to have a fundamental rule against naked singularities. This is the principle of cosmic censorship, a bold conjecture that nature abhors a singularity visible to the outside world. It suggests that every singularity must be cloaked and hidden safely behind an event horizon, its infinite density and unpredictable physics forever sealed away from the rest of the cosmos. Think of it as the universe's own fail-safe mechanism. Without this cosmic veil, the orderly fabric of cause and effect could unravel. The laws of physics, which break down completely at a singularity, would no longer be confined. The result would be pure chaos, with unpredictable gravitational forces and bizarre phenomena erupting into our universe without warning. But is this censorship law always enforced, or could a black hole lose its event horizon, exposing the raw singularity within? The mathematics of general relativity allows for this possibility under extreme conditions, like if a black hole spins fast enough or swallows a very specific type of matter. Most physicists believe some unknown physical law prevents this from ever happening, that the cosmos actively protects its deepest secrets from view. Yet the question remains a profound unknown, forcing us to wonder if the universe's most dangerous secret is permanently locked away, or if there is a key we have not yet found. While the singularity remains hidden, a rotating black hole reveals another spectacular region just outside its event horizon, a place where the fabric of reality is set into motion. This is the ergosphere, an oval-shaped region of distorted spacetime where the black hole's immense spin drags everything along with it. Imagine trying to stand still in a powerful whirlpool, the current tugging relentlessly at your feet. In the ergosphere, spacetime itself is that current, and it is flowing faster than the speed of light. Nothing can resist being swept along in this cosmic dance. You are no longer an observer of space. You are a passenger on a river of spacetime that is rushing around the black hole. This incredible property is not just a curiosity, it is a potential power source of unimaginable scale. The physicist Roger Penrose realized that this rotational energy could be stolen. In the Penrose process, an object enters the ergosphere and splits in two. One piece is deliberately sent plunging into the black hole, following the inward flow of spacetime, while the other piece escapes with more energy than the original object had. It seems like magic, creating energy from nothing, but the energy is borrowed directly from the black hole's own spin. The infalling piece carries negative energy, effectively slowing the black hole's rotation, and that stolen rotational energy is given to the escaping fragment. A civilization advanced enough to harness this could, in theory, mine a black hole for power, slowly breaking its spin until it becomes a non-rotating remnant. The ergosphere is a testament to the dynamic, almost living nature of these cosmic giants, a place where space-time is not a static stage but a swirling, energetic fluid waiting to be understood. There seems to be no ceiling to a black hole's appetite. We find stellar black holes, the collapsed cores of giant stars, weighing in at a few dozen times the mass of our Sun. Then we leap in scale to the supermassive monsters anchoring galaxies, some with masses of millions or even billions of suns. But could there be something even larger, an ultramassive black hole tipping the scales at tens or hundreds of billions of solar masses? Theoretically, there might be an upper limit. A black hole's feeding frenzy is thought to be self-regulating. As matter spirals inward, it heats up, emitting intense radiation and powerful jets that can push away the very gas and dust the black hole needs to grow. This creates a kind of cosmic feedback loop, a natural brake on its expansion. Yet, in the early universe, conditions were so dense that these limits might have been overcome, allowing for the birth of true behemoths whose shadows we have not yet seen. The question of a maximum size is ultimately a question about the environment, a cosmic battle between gravity's relentless pull and the furious energy of its own feast. While we ponder their potential growth, we must also confront their inevitable end. Every black hole, from the smallest primordial speck to the largest galactic giant, is slowly evaporating through Hawking radiation. For almost all of its life, this is an imperceptible drip. A stellar black hole might take a number with 67 zeros years to evaporate, a timescale so vast it dwarfs the current age of the universe. But the final act is a runaway process. As the black hole shrinks, its temperature soars, and the rate of radiation explodes. In its last second of existence, a black hole with the mass of a mountain would release the energy of 1,000,001 megaton hydrogen bombs. And then it vanishes, or does it? The ultimate fate is a deep mystery. Does the evaporation continue perfectly until the black hole winks out of existence, leaving nothing behind? Or does the process halt at the very end, leaving a stable, microscopic relic, a frozen cinder containing the final scraps of information from everything it ever consumed? Our current theories of gravity and quantum mechanics offer no clear answer. The final flash might be the ultimate erasure, or it might be the creation of the universe's most permanent and enigmatic fossil. The journey toward a black hole's singularity might not be an ending, but a new genesis. Some of the most daring theories in cosmology suggest that the violent collapse that forms a black hole in our universe could trigger an inflationary Big Bang, birthing an entirely new cosmos within. This idea transforms a black hole from a cosmic dead end into a potential gateway, a one-way portal to a universe with its own unique laws and constants. In this breathtaking multiverse scenario, every black hole could be a separate universe in the making, with our own cosmos perhaps originating from the singularity of a black hole in apparent reality. This speculative vision, emerging from the edges of quantum gravity and inflation theory, presents a cosmos of infinite regress, a great cosmic matryoshka doll of nested realities. The implications are staggering, suggesting that the laws of physics we hold as fundamental might simply be local bylaws, the unique outcome of our particular cosmic birth. Yet if a black hole is a gateway, what happens to the identity of what falls in? This brings us back to the information paradox with a new and startling perspective. The principle of black hole complementarity offers a radical solution, proposing that there is no single objective truth about what happens to an object crossing the event horizon. From the perspective of an outside observer, the object is vaporized and its information smeared across the horizon's surface, never actually entering the black hole. But from the perspective of the object itself, it passes smoothly through the horizon, unaware of its own fiery doppelganger. Both stories are simultaneously true, not because the universe is inconsistent, but because the information describing the event is complementary. No single observer can ever witness both fates, preserving the consistency of physics from every possible viewpoint. This bizarre duality finds an even deeper mathematical connection in the ER equals EPR conjecture. This idea proposes a profound link between two seemingly unrelated concepts: quantum entanglement, symbolized by EPR, and wormholes, known as Einstein-Rosen bridges or ER. It suggests that every pair of entangled particles, though spookily connected across vast distances, is in fact linked by a microscopic wormhole. For a black hole, this implies that the Hawking radiation particles emitted as it evaporates are not independent. Each escaping particle could be intricately entangled with another particle deep inside the black hole, or with the radiation emitted earlier via a complex web of these space-time tunnels. Information would not be lost or stored on a surface, but subtly transmitted through these hidden geometric connections in the fabric of reality. The black hole's interior and the external universe remain inextricably linked, not by a single bridge we could traverse, but by a vast, invisible network of quantum threads woven into the space-time continuum itself. The event horizon is not a wall of fire or a simple boundary, but the entrance to an impossibly complex tapestry of connections, where information is preserved not in a place but in a relationship. These cosmic giants may even hold a key to the universe's ultimate fate. Dark energy, that mysterious force causing the expansion of the universe to accelerate, operates on the grandest scales. Black holes, in contrast, are masters of local collapse, pulling space inward with immense gravity. The relationship between the two is a profound puzzle. Could the energy contained within black holes somehow be linked to the dark energy driving the cosmos apart? One controversial idea suggests that the vacuum energy inside black holes might contribute to the overall dark energy budget. It is a cosmic tug-of-war writ large, the universe's relentless outward push against the most powerful inward pull in nature. Understanding this dance could reveal whether dark energy is a constant force or something that evolves, intimately connected to the life and death of the universe's most massive objects. This leads to another startling possibility on the scale of entire galaxies. What if a galaxy's core was not dominated by a single supermassive black hole, but by a dense swarm of them? Imagine a black hole galaxy, a cosmic realm where thousands or even millions of black holes orbit one another in a dark, chaotic dance, with very few stars to light the void. Such a place would appear strangely dark and massive, its true nature hidden from conventional telescopes. The gravitational tugs between these countless black holes would create a shimmering, invisible core, a perfect hiding place for dark matter. If such galaxies exist, they would force us to completely rethink how galaxies assemble. They might be the ancient, fossilized remains of the first star clusters, where countless massive stars lived fast, died young, and left behind a legacy of darkness. Finding one would be like discovering a ghost city, its streets empty but teeming with invisible, massive inhabitants. The hunt for these shadow galaxies is on, pushing our telescopes to peer into the darkest, most quiet corners of the cosmos, searching for the subtle tells of a universe built not on light, but on gravity's pure, dark signature. While the final evaporation of a black hole is a quantum whisper, its formation might shout the secrets of quantum gravity. Physicists are listening intently for these signatures, specific patterns in the Hawking radiation or subtle vibrations in the event horizon that could only be explained by a unified theory. It would be like finding a fossil with a structure that no single known law of nature could have created, a clear imprint of both gravity and quantum mechanics working in concert. The precise spectrum of the radiation, or the way a black hole rings like a bell after merging with another, could carry these encoded messages from the edge of known physics. Discovering such a signature would be the key to a new realm of understanding, finally linking the universe of the very large with the very small. From this quantum edge, we step back to witness a distortion of time itself. The gravitational grip of a black hole stretches time in a way that defies intuition. Imagine two identical clocks, one placed on a spaceship hovering perilously close to the event horizon, and the other safely back on Earth. You watch them both from afar. The clock near the black hole would appear to tick agonizingly slow, its second hand crawling while the Earth clock spins at a normal rate. This is time dilation, an effect predicted by Einstein taken to its absolute extreme. For the astronaut by the black hole, their own time feels normal, but the entire external universe would appear to speed up into a blinding high-energy blur. Stars would be born, live, and die in what seems like moments. Galaxies would whirl and merge in a frantic dance. From that perspective near the precipice, you would witness the ultimate fast-forward of cosmic history, a silent, spectacular light show of billions of years unfolding before your eyes in a matter of hours or days. The philosophical weight of this is staggering. Which timeline is real? Is your subjective experience of a minute more valid than the universe's objective passage of an eon? The black hole does not answer. It only demonstrates that time is not a universal constant, but a personal, pliable experience, warped by gravity into something deeply and fundamentally relative. Even the strangest cosmic objects might share a deep connection with the simplest electrical parts. A memristor is a theoretical fourth fundamental circuit element, distinct from the resistor, capacitor, and inductor. Its unique property is a memory. Its electrical resistance changes based on the history of the current that has flowed through it, and it remembers that history even when the power is switched off. Now, some physicists have proposed a staggering parallel, that a black hole might behave like a cosmic-scale memristor. The black hole's event horizon, according to this speculative idea, does not just store information, it dynamically adjusts its properties based on what has fallen in. The flow of matter and energy into the black hole is like the electrical current, and the resulting changes to the horizon's properties, perhaps its size or its internal quantum state, represent the memory. Each star consumed, each particle captured, would leave a permanent, if subtle, mark on the black hole's effective resistance, creating a cosmic ledger of its entire accretion history. This is not just a simple storage of data, but a functional memory that could potentially influence how the black hole interacts with future infalling matter. It transforms the black hole from a passive pit into an active component in the circuit of the cosmos, one that remembers everything it has ever touched. While a memristor stores information, another theoretical construct could weaponize energy itself. Imagine building a giant, spherical mirror around a black hole, creating a cavity that perfectly traps light and radiation. Now send a single wave of light into this cavity. Due to a remarkable effect in the black hole's ergosphere called superradiance, the wave can extract a tiny bit of the black hole's rotational energy as it scatters. Normally, this energy would be lost to space, but inside our perfect mirror, the amplified wave is reflected back toward the black hole. It enters the ergosphere again, gains even more energy, and is reflected again. This process creates a runaway feedback loop, a chain reaction of exponentially growing energy trapped inside the mirror. The waves become so intense that they no longer behave like light, but like a raging ocean of raw power, building pressure with every pass. This is the principle of the black hole bomb. The containment mirror would not hold forever. The exponentially rising energy would eventually shatter the mirror itself, releasing a cataclysmic explosion, a flash of energy that could outshine entire galaxies. This is not science fiction, but a terrifying possibility allowed by the pure mathematics of general relativity. It reveals that black holes are not just power sources, they are potential amplifiers, and if nature were ever to construct such a resonant chamber, the resulting detonation would be one of the most violent events since the Big Bang. The enigma of the supermassive black hole's birth is written in the ancient light of the first galaxies. We find these behemoths weighing billions of times our sun's mass, already fully formed when the universe was a cosmic toddler, barely a billion years old. Their very existence is a profound timing problem. How could they gather so much mass so quickly? There are two leading theories in a race against time itself. One suggests they were born big from the direct collapse of colossal primordial gas clouds. In this scenario, a vast cloud would skip the star-making process entirely, collapsing under its own immense weight directly into a massive seed black hole, 1,000 times heavier than our Sun from its very first breath. The other theory proposes a slower, more violent assembly line, where the first generation of stellar black holes merged and cannibalized each other, growing rapidly in the dense stellar nurseries of the early universe. Yet even this frantic merging struggles to explain the largest giants we see. The truth may be a chaotic combination of both, a feeding frenzy in a universe young and dense enough to sustain it, leaving us to wonder what extreme conditions could forge such perfect cosmic predators in mere moments after the dawn of time. This puzzle of their immense scale leads directly to a question about their most intimate details. For decades, the no-hair theorem painted them as perfectly simple, defined only by mass, spin, and charge. But what if that cosmic barbershop left a subtle stubble after all? New theoretical work is challenging this classical view, suggesting that black holes might possess quantum hair. This is not hair you could see or touch, but a delicate, complex structure imprinted on the gravitational field surrounding the black hole, a faint fingerprint left by everything that ever fell in. This quantum hair would be a way for the black hole to retain information about its history without violating the laws of physics, a permanent, if incredibly subtle, memory of its past. It would mean that no two black holes are truly identical, even if they share the same mass, spin, and charge. Their unique formation stories and everything they have consumed would be etched into their very essence, written in a language of quantum gravity we are only just beginning to decipher. The search for this hair is a hunt for the universe's most permanent ink, a record of cosmic history hidden in plain sight, woven into the fabric of space-time itself. The relentless forward march of time might find its ultimate expression in the depths of a black hole. Our universe has a distinct direction, an arrow of time pointing from a past of low entropy, like a pristine, unbroken egg, to a future of high entropy, the inevitable scrambled mess. A black hole, with its colossal entropy written on its event horizon, represents one of the most disordered states possible. It is a powerful sink for this cosmic arrow, a destination where order is not just broken but fundamentally erased. Some physicists wonder if the very existence and relentless formation of these entropy giants is what helps drive the arrow of time forward on a universal scale, creating a cosmic bias toward disorder from which there is no return. While this connects black holes to the most fundamental law of our reality, a recent image brought their shadowy presence into stunning focus. The first picture of a black hole's shadow, captured by the Event Horizon Telescope, was not a picture of the black hole itself, but of its absence, a dark silhouette encircled by a brilliant, lopsided ring of fire. That luminous ring is the photon sphere, a region where gravity is so intense that photons of light are forced to orbit the black hole, some escaping after multiple loops to reach our telescopes. The precise shape and brightness of that ring are not arbitrary. They are a direct fingerprint of the black hole's ferocious spin and the intense warping of space-time around it. Subtle distortions in that ring of light could reveal the hidden presence of exotic physics, perhaps even the faint whispers of quantum gravity or the turbulent swirl of the accretion disk's magnetic fields. Future telescopes with even sharper vision will read this shadow like a cosmic scrying glass, searching for the tiny flickers and asymmetries that betray secrets we can currently only theorize. What unknown laws are written in that perfect circle of darkness, and what will we learn when we can finally read them? Two of the most violent objects in the universe are destined for a catastrophic dance. When a black hole's event horizon meets the super-dense crust of a neutron star, the result is a spectacle of pure cosmic destruction. We do not yet know the precise choreography of this merger. Does the neutron star, a city-sized object heavier than our Sun, simply plunge into the black hole in one silent, dark gulp? Or does it resist, its incredible density causing it to be torn apart just outside the horizon, creating a brief, hyper-dense hybrid object, a black hole temporarily wearing a shroud of disintegrating neutron matter? This fleeting state would be a laboratory of extreme physics, where matter is squeezed beyond the limits of atomic nuclei. The true answer is written in the ripples of space-time itself. Gravitational waves from such a collision would carry a unique signature, a rising chirp followed not by a clean cutoff, but by a complex after-ring. This signal would tell us about the neutron star's internal composition, its stiffness, and how it fought against the tidal forces of the black hole until the very last moment. Each collision is a unique experiment, revealing the behavior of matter under conditions we could never recreate on Earth. From this violent processing of matter, we turn to a more abstract form of computation. Could the same event horizon that scrambles information also be performing the most complex calculation in nature? The holographic principle suggests that a black hole is a perfect information processor. Every bit that falls in is encoded onto its surface, and the way that information is scrambled and redistributed is a form of natural computation. This has led to the staggering idea that black holes might be the universe's ultimate quantum computers. Their event horizons could be acting as quantum circuits, processing the information of everything that falls in with maximum efficiency. The immense entropy of a black hole is not just disorder, it is a measure of its hidden computational power. If this is true, then the limits of computation are not set by human-made silicon chips, but by the fundamental laws of physics as embodied by these cosmic giants. It means that the universe is not just storing data, it is constantly running programs on the hardware of space-time, with black holes as its most powerful processors. What cosmic algorithms are they running, and what is the final output of a calculation that has consumed stars? The final whisper of a black hole's existence is its most profound secret. After countless eons of slowly leaking its mass away as Hawking radiation, the black hole enters its final, frantic moments. Its size shrinks from stellar scale to something smaller than an atom, its temperature skyrocketing into the billions of degrees as the radiation intensifies into a blinding flash. Then it approaches the Planck mass, a tiny fundamental unit where the classical idea of gravity gives way completely to the quantum realm. At this precipice, our known physics dissolves into pure uncertainty. We face three stark possibilities for this ultimate endpoint. The first is complete evaporation, a true vanishing act. The black hole radiates its very last joule of energy and simply winks out of existence, leaving behind only empty space. It would be the ultimate erasure, a cosmic delete button pressed on a once dominant object. The second hypothesis proposes a stable relic. The evaporation process halts, leaving behind a permanent, indestructible fossil, a particle of Planck mass that contains the final, locked-in information of everything the black hole ever consumed. This remnant would be a frozen cinder, a time capsule from the death of a universe. The third and most speculative possibility is a quantum bounce or a phase transition. Instead of vanishing, the extreme conditions could trigger a new kind of physics, a violent rebirth where the black hole transforms into something else entirely, perhaps even a white hole, explosively spewing its contents back out into the cosmos. The reason this endpoint remains a towering unknown is that it is the one place where general relativity and quantum mechanics are both screaming for dominance, and we simply do not have the language to listen to both at once. The final flash is not just an ending, it is a gateway to a new law of physics, a single, brilliant point of light whose aftermath holds the answer to how the universe truly handles its most extreme information. When two black holes spiral toward their final union, they do not simply collide like billiard balls. Their event horizons stretch and distort, reaching for one another across a gap of warped spacetime until they touch and merge into a single, oscillating horizon. This final, violent act is the merger ringdown, a phase where the newborn black hole shudders and vibrates, shedding its imperfections in a storm of gravitational waves. These are not simple waves, they are the complex fingerprint of spacetime itself being stretched and squeezed. The specific frequencies and decay rates of these vibrations, the way the black hole rings down to silence, are a direct test of general relativity's predictions. If the ringdown contains unexpected tones or lasts too long, it could be the first hint of new physics, a sign that Einstein's theory, for all its brilliance, needs an adjustment in the most extreme gravitational fields. Think of it like striking a bell. A perfect bell made according to known laws will ring with a pure, predictable tone that fades in a specific way. But if the bell is flawed or made of an unknown material, its ring will sound different. The merger ringdown is the universe striking its most massive bell, and we are just learning how to listen. Supercomputer simulations show this cosmic dance in stunning detail, visualizing the event horizons as they merge into a single, lopsided object that rapidly settles into a perfect sphere. The gravitational waves produced carry away a staggering amount of energy, more than all the stars in the observable universe emit in that same moment. Their precise shape encodes everything: the masses of the original black holes, their spins, and the very geometry of the region where they merged. Each detection is a message from the edge of known physics, a ripple that might contain the secret signature of extra dimensions or the faint echo of quantum gravity. What ultimate truth about the fabric of reality is being woven into these invisible tremors, and what will we hear when our listening becomes sharp enough to understand its every note? These cosmic blowtorches, visible across millions of light years, are the universe's most powerful particle accelerators. Erupting from the poles of voracious supermassive black holes, jets of plasma scream into the void at nearly the speed of light, sculpting entire galaxies with their raw fury. The mystery is not just their power, but their precision. How does the chaotic inferno of a black hole's accretion disk, a swirling maelstrom of superheated gas and dust, give birth to these perfectly focused beams? The leading theory points to the black hole's own spin and the intense magnetic fields it generates. As the black hole rotates, it twists the surrounding space-time, and the magnetic fields frozen within its accretion disk into a tightly wound coil. This creates a colossal, natural particle gun. Some of the infalling matter, instead of crossing the event horizon, is caught by these magnetic field lines and funneled toward the poles. There, it is launched outward in two opposing, incredibly narrow jets, like water forced through a cosmic nozzle. Yet the exact trigger that starts this process and keeps the beam so tightly collimated over distances larger than entire galaxies remains one of the great puzzles of high-energy astrophysics. These are not gentle streams but cosmic tsunamis of energy. The Chandra X-ray Observatory reveals them as titanic columns of million-degree gas punching through intergalactic space. The Hubble Space Telescope shows their stunning visual impact where these jets slam into clouds of cooler gas, creating brilliant, glowing cavities that stretch for thousands of light years. This is where the black hole's influence transcends its local space and dictates the fate of its entire galactic home. When these jets plow into galactic nurseries, the giant clouds where stars are born, they do something paradoxical. They can both trigger and quench star formation. The initial shockwave can compress gas, causing it to collapse and ignite new stars in a burst of creation. But the jets also deliver a torrent of heat and turbulence, blowing the galactic gas reservoir away and shutting down star formation for eons. A supermassive black hole through these jets can effectively sterilize its own galaxy, preventing new stars from ever being born. It is a feedback loop of breathtaking scale, where a single object at a galaxy's core can dictate its life cycle, all through these focused beams of pure energy. What other cosmic balances are being maintained by the silent, invisible push of these distant jets? Perhaps the most radical unknown is whether black holes are not just objects within space-time, but the very substance of it. We think of space as a smooth, continuous stage and time as a flowing river, but what if reality is fundamentally pixelated? Theories like loop quantum gravity propose that space-time itself is woven from a fabric of finite, incredibly tiny loops, a billion times smaller than an atom. In this view, the universe is not a smooth sheet but a dynamic, shimmering network of discrete connections. A black hole, then, might be a place where this underlying fabric is pulled so taut that its fundamental threads become visible. The event horizon could be a boundary where the weave of this network is stretched to its limit, and the immense entropy of a black hole, proportional to its surface area, might be a direct count of the number of these fundamental spacetime atoms that make up its boundary. This transforms the black hole from a cosmic object into a cosmic microscope. The way a black hole evaporates, the specific spectrum of its Hawking radiation, and the precise tones of its merger ring-down could all carry the faint signature of this quantized structure. It would be like listening to the sound of a bell to determine the atomic structure of the metal it is made from. The subtle differences between a smooth spacetime and a pixelated one would imprint themselves on every aspect of a black hole's behavior. If we could detect these tiny deviations, we would be witnessing the atoms of reality itself. Are we living in a continuous universe, or is everything we see and feel, from the farthest galaxy to the passage of a single second, ultimately emerging from a vast cosmic digital display? Black holes might be the one place in the universe where we can read the resolution. We have traveled from the crushing fate at the singularity to the slow, quantum whisper of Hawking radiation, a journey through 30 staggering mysteries that define the frontier of our knowledge. These cosmic giants are far more than simple vacuum cleaners of space. They are active, dynamic laboratories where the deepest laws of physics are written in extreme gravity and quantum code. Each unknown, from the Firewall paradox to the nature of the final flash, is not a dead end but a signpost pointing toward a greater truth we have yet to grasp. They teach us that our universe is stranger, more interconnected, and more mysterious than we ever dreamed. The story of black holes is ultimately the story of our quest to understand reality itself. So we turn the question to you: of all these profound unknowns, which one baffles you the most? Which mystery of the cosmos keeps you wondering? Share your thoughts in the comments below. If you enjoyed this deep dive into the abyss, please like this video and subscribe for more adventures into the heart of the universe's greatest mysteries.